Hello, my name is Jonathan Ressert, and today we'll be presenting our work on the robustness of offensive language classifiers. Please note that later on we view text which may be offensive to some. Please keep this in mind as you proceed. First, what is an offensive language classifier? An offensive language classifier takes text as an input and outputs whether or not the text is offensive. Now, why would we like to classify offensive language? On social media, some users try to attack others by posting offensive or hateful comments. To combat this, social media sites often deploy automated offensive language classifiers to identify these comments and stop the user. However, users who are trying to attack others via offensive language may be crafty in the way they reply and change their comments to hide their offensive language in plain sight. For example, replacing characters with visually similar characters or using non-common slurs. The current state-of-the-art offensive language classifiers may not be prepared for these changes and allow offensive text through. Thus, in this work, we evaluate the robustness against a crafty obfuscation algorithm which leverages human knowledge to attack. For our threat model, we assume that the adversary's goal is to modify their offensive post in such a way which evades detection by offensive language classifiers, while also preserving semantics and readability for humans. To make modifications, the adversary is assumed to have black box access to a surrogate offensive language classifier that differs from the one used by the social media platform. The adversary uses feedback from the surrogate classifier to guide modifications to the text. Our goal is to evaluate how well the adversary can evade detection under this threat model. We examine the robustness of 5 different offensive language classifiers. First, we examine 3 classifiers which achieved top results in OffensiVal, which was a collaborative workshop in identifying offensive language. 2 of these systems achieved the top 2 ranks, and both leveraged BERT in their methods. The third was the top-ranked non-transformer based system. It is a voting ensemble of 3 deep learning models, a CNN, a BLSTM, and a BLSTM fed into a B-GRU. For the fourth classifier, we use a lexicon of offensive language. A text is considered offensive if it contains one of the words from this lexicon. For the fifth classifier, we leverage Perspective API, which is an API created in collaboration between Jigsaw and Google. Perspective assigns a toxicity score to an input text. Following previous work, we labeled those texts with greater than 0.5 toxicity scores as offensive. Next, let's examine our proposed attack. Our proposed attack can be divided into 2 main steps, selection and replacement. In the selection step, our goal is to determine which words from the original text should be replaced. We examine 2 approaches for selection, a greedy approach and an attention approach. For the greedy approach, we first remove each word one at a time, but still retain the rest of the text, and get the drop in classification probability for the text from the surrogate classifier. The words with the highest drop in probability is our first choice to replace, and it is set aside. We repeat this process until the label is flipped from offensive to non-offensive. The words which were removed in this process make up the full list of possible replacements. For the attention selection approach, we leverage a BLSTM with attention, which has been trained to identify offensive language. To select words, we give input text to the BLSTM and examine the attention weights estimated during classification. The word with the highest attention weight is selected for replacement. If this is insufficient to flip the label, the next highest weighted word is selected, and so on. Next, we examine the replacement step. First, a list of the 20 most similar words is obtained from an embedding space. Next, we replace the selected word with its most similar word and check this against the surrogate classifier. If the text is found non-offensive, then the word is chosen. Otherwise, the process continues with the next most similar word. If none of the most similar words cause the surrogate classifier to misclassify, then we choose the replacement word which causes the highest drop in classification probability. Let's examine the embedding space from which we draw replacement words. As a reminder, our goal is to design an attack which chooses crafty words for replacement. To this end, we first build a text collection of 13 million deleted tweets using the Twitter API. Next, we filter out tweets from the set that are labeled as offensive by any of our offensive language classifiers. The remaining 8.5 million deleted tweets contain offensive text, which was likely flagged by users or human moderators. We expect this set of deleted tweets to contain crafty substitutions, which are able to evade detection by state-of-the-art offensive language classifiers. We refer to this set of tweets as the evasion collection, and it is used to train word embeddings. We examine substitutions with both a glove pre-trained Twitter embedding as well as a version of that same embedding fine-tuned on the evasion collection. We compare our approach with two other attacks. The first, Viper, randomly replaces characters in the text with visually similar neighbors determined from a visual embedding space. For the second, we explore whitespace attacks proposed by previous research, which adds whitespace after every character, and a similar attack which removes all whitespace. Additionally, that same approach tests adding the word love to hateful text to attack them, so we try this approach as well. For our experiments, we examined two offensive language datasets. The first dataset, OLID, was used to evaluate systems in Offensive-Eval 2019. The second dataset, SOLID, is an expansion of OLID and used as evaluation in Offensive-Eval 2020. We evaluate the attack using two metrics. First, we measure the drop in accuracy caused by the attack. Second, since the adversary still wants the text to be understandable by humans, we measure readability and semantic preservation. Here we find our main results of the proposed attack on OLID and make several key observations. First, the offensive language classifiers are indeed susceptible to our adversarial attacks. This can be observed in the drops in accuracy seen across the table. Specifically, 50% of attacks cause a drop of 24 points or more, and 69% cause a drop of 20 or more. We also observe that the greedy select outperforms the attention select. Finally, the pre-trained embeddings and fine-tuned embeddings find success against different systems. Specifically, we see that the fine-tuned embeddings do well against the BERT-based systems, while the pre-trained embeddings do well against the other three. For robustness, we find that the BERT models make up the most susceptible and most robust systems at the same time. We find Newly to have the lowest drop in accuracy of 26. We find Veradichev to both achieve the original highest accuracy, but also be the most vulnerable to attacks, with an average drop in accuracy of 37, the highest of any of the offense language classifiers. We believe the stark difference between the two systems is related to their preprocessing steps. For example, Newly's preprocessing step adds in additional context by converting emojis into text. However, Veradichev's removes stop words, which could hinder BERT, which is a context-aware system. Then, as the attack is more likely to change non-stop words, Veradichev will lose both contextual information as well as offense indicating tokens. For surrogate classifiers, we find that Newly is the most helpful in causing accuracy drops against other classifiers. For the other attacks, we find that simple preprocessing is able to mitigate them. For the whitespace attacks, those classifiers which leverage word segmenters were the least affected by the attack. For the character replacement attacks, we found that adding a preprocessing step which replaces non-common characters with common characters was enough to greatly reduce its effectiveness. We note that unlike these attacks, there is no simple preprocessing step to mitigate against the fine-tune embedding approach. For the solid dataset, we observed similar success of attacks for our approach. Specifically, 75% of attacks cause a drop of 40 or more, and all attacks cause a drop of at least 33. For readability, we asked 3 crowd workers to annotate 50 tweets which were modified by our approach. For comparison, we also asked additional crowd workers to evaluate the readability of the original text. For semantic integrity, we asked 3 different crowd workers if the modified text conveyed the same meaning as the original. Finally, for each tweet, we combined the crowd workers' votes by taking a majority vote. Our results show that the fine-tune embedding drops readability only slightly from the original, while still maintaining much of the original meaning. We specifically see that the readability drops by 4%, however, close to 2/3 retain the same meaning, and 96% of the tweets retain at least partial meaning. We can also get a sense of meaning preservations by observing the tweets which were annotated by the crowd workers. These drops in accuracies, as well as the ability to maintain readability and meaning, show the strength of our proposed attack. We further examine the fine-tune embeddings for additional analysis. To do this, we use a lexicon list of offensive words. We obtain the 20 most similar words for both the pre-trained and fine-tune embeddings. We then use perspective to determine the rank at which the first evasive word is found for each embedding. We find that on average, the fine-tuned embedding has an evasive word much closer to the original word than the pre-trained embedding. Specifically, for the fine-tuned embedding, the evasive word is 3 ranks away, while for the pre-trained, it is 11 away. This means that the fine-tuned embedding will find the evasive word more quickly than the pre-trained. Thus, we observe that offensive language classifiers are vulnerable to crafty attacks which are able to both drop accuracy and maintain meaning and readability. Furthermore, unlike the compared attacks, our proposed attacks cannot be easily mitigated via preprocessing. For future work, we like to improve the robustness of offensive language classifiers against our attack by leveraging adversarial training. Specifically, since the attack relies on the evasion collection which contains crafty adversarial examples, offensive language classifiers can incorporate the latest version of the evasion collection into their training.